Today, Brian, and he's going to tell us magneto-gravitational trapping of silicon particles containing silicon vacancy centers. Please, Brian, the floor is all yours.
All right, thank you. So first, I'm not actually going to get to the silicon carbide particles and the silicon vacancy centers until the end of the talk. So there's a fair amount of background to go through before then, but I'll try to get through it as quickly as possible. So the motivation for our experiments are, like many of us, doing sort of tabletop gravitational measurements that range from tests of macroscopic quantum mechanics to, in our case, precision measurements of big G, the Newtonian constant of gravitation, as well as high sensitivity force measurements. And so our motivation for pursuing levitated optomechanics as a way of doing these measurements is, I think, pretty typical. Cold atoms are in many ways our competition, but of course their tiny mass makes gravitational forces really weak. So that's one of the nice things about these trapped particles is they're so much more massive. Compared to clamped systems like MEMS or NEM systems, we of course at least hope to have a lot less loss or higher Q because there's no clamping in the system. And then a third motivation for us, particularly for precision measurements, is that if you have spheres, or ideally spheres that you're trapping, it's a nice simple geometry and it makes precision measurements convenient in many cases. Of course, one thing I'm going to come to a little bit later is that our particles are, of course, not perfectly spherical, and it actually causes us some difficulties. So what's hard about this? Well, the force of gravity is, of course, very weak. It's particularly weak on small particles. There's no way to shield against gravity, so that means that we have to worry about things like, in my case, undergraduates getting out of the lecture hall across the hall from my lab and walking through the hallway, and what impact do they have on our experiments as they walk by, their gravitational attraction, what effect it has. And third, the equivalence principle, since accelerations are indistinguishable from gravity, it causes some weird effects like sensitivity to non-inertial reference frames. And we've had to have the odd conversation in my lab of, wait a minute, which way really is the axis of rotation of the Earth in our lab frame, and what impact does that have on some of the experiments? So there's funny stuff like that you have to deal with in these measurements. So there are three, I would say, primary approaches to levitated optomechanics right now. The first is, of course, optical traps, pioneered by Arthur Ashkin. So his paper came out in Phys Rev Letters in 1970. He won the Nobel Prize in 2018 for work on optical tweezers. Paul traps, or electrodynamic traps, were first described around 1953. Of course, Wolfgang Paul and Hans Dehmelt won the Nobel Prize in 1989 for that. And the third technique, which is the one that my group pursues, is using static magnetic fields to make traps for diamagnetic particles. And this was sort of at least popularized by Michael Berry and Andre Geim in 1997, where they levitated a frog in an 18 Tesla high field magnet. And following the similar pattern, they won, in this case, the Ig Nobel Prize in 2000. Of course, Andre Geim went on to win the Nobel Prize for graphene, but not for levitating frogs or anything. So we use this technique of levitating things with magnetic fields, and hopefully we won't just win an Ig Nobel Prize. But okay, so the rest of my talk will start with an introduction to these traps. I'll try to get through that pretty quickly. What we're trying to do is measurements that approach the standard quantum limit, but there's sort of a question of what standard quantum limit or what measurement are we actually trying to do? I'm going to talk a little bit about classical measurements that we're making of ultimately big G and also local acceleration in our lab. That's partially because that turns out to be a useful technique, or there's some useful techniques there that we developed for doing more quantum gravity related work. And finally, I want to talk about trapping silicon carbide particles and using defect states in them, in particular silicon vacancies, to try to start doing some real quantum measurements in these systems. So let me start with the introduction to the traps. So this is the kind of trap we use. We call it a magneto-gravitational trap. It uses a magnetic quadrupole field to levitate the particles with a field gradient of about a Tesla per 100 microns. So it's a pretty strong field gradient made with permanent magnets. We just use samarium cobalt magnets, as well as some ferromagnetic pole pieces. We typically use an alloy for the pole pieces called Hyperco 50, which has the highest saturation magnetization available in a commercially produced alloy. That magnetic quadrupole produces a a trap only in 2 dimensions. It's really just a linear quadrupole. To add a 3-dimensional trap, we make the top pole pieces shorter than the bottom ones, and that makes the zero field region curve upward as you move out of the center of the trap along the axis of the trap. And the result of that is that Earth's gravity actually holds the particle in the 3rd dimension, which is why we call it a magneto-gravitational trap. The motivation for making a trap this way is, for one, we can make a stronger 2-dimensional quadrupole. And secondly, the highly anisotropic trap results in 3 essentially independent oscillation frequencies. So it's easy to distinguish the oscillation frequencies in the 3 directions in the trap. In terms of modeling these traps, we use some finite element calculations to model the fields, but we also often use a very simple model that's just a 3-term spherical harmonic expansion of the magnetic field, which I show in the bottom here. On the left is the magnitude of the magnetic field, either looking down the axis of the quadrupole or looking perpendicular to that. You can see this sort of smile-shaped region, which is the zero field region in the quadrupole that curves up as you leave the center of the trap. When you then include Earth's gravity, you can calculate the total potential energy of a particle in the trap. And you can see it again. It's trapped in the along the axis of the quadrupole, but then in the other direction is trapped by the addition of gravity. So that makes a weak, broad trap in this, what we call the axial direction in the trap, where the Earth's gravity is used to provide the trap. Okay, so that's the basics of the trap. Experimentally, here's some pictures of our system. In the upper left here, I've got the trap itself. You see the 4 pole pieces coming together as a quadrupole. There's a very small gap of on the order of 100 or a few hundred microns between the pole pieces in the center there. Going down from there, you can see through the front chamber of the front window of the vacuum chamber, you can see the pole pieces. And then on the right is our chamber and the vacuum pump surrounding it. Typically, this system is pumped down with a turbo pump, but then after baking, we switch to pumping with an ion pump and a titanium sublimation pump. And that lets us get to ultra high vacuum. And we physically remove all of the mechanical pumps or all the connections to mechanical pumps from the system to eliminate vibrations from the system. Even though in principle, turbo pumps should be okay because of their high rotation frequency, we still find them to be a problem in practice. So that lets us get to ultra high vacuum, which for us is something better than about 10 to the minus 10 torr. At that point, we can no longer measure our vacuum well for technical reasons. We can't put an ion gauge on our chamber because it tends to knock our particles out. Okay, so here's some of the general features of these kinds of traps that we've developed over time. I'm just going to summarize them all together. I've talked about these lots of times before, and many of you are probably familiar with them. We can trap particles from about 1 to about 65 microns in diameter. We can probably go bigger if we really wanted to, but we tend to start crashing into the pole pieces and things like that. On the low end, the 1 micron diameter end is limited by the fact that for smaller particles, the thermal motion gets to be large enough that it can escape the trap, particularly in this axial direction. If we really wanted to, we could probably build a trap that could hold smaller particles. It just gets harder and harder, and the thermal motion of the trap of the particles gets to be very large, particularly in that one direction. We can trap a huge variety of materials. It turns out that most materials are weakly diamagnetic, and that includes materials like silica, which is probably our favorite trapping material, silicon carbide. We've trapped diamond. We can trap water. Of course, it evaporates in vacuum. Oils, we've actually found some oils that hang around for quite a long time, even under high vacuum. So all materials like that work. The oscillation frequencies in our trap are typically really low. So in this axial direction, that's the direction that's held in by gravity, the oscillation frequencies can typically be from about 1/10 of a hertz up to about 10 hertz. And we have reason for some precision measurements to push that lower. So we're actually trying to get to significantly lower than 1/10 of a hertz. And on the high end, we could probably go a little bit higher if we wanted, but this is sort of the typical range. The other 2 directions, which we call the transverse direction and the vertical direction, vertical is up and down relative to Earth's gravity. The oscillation frequencies typically range from about 50 to 120 hertz. Unfortunately, sometimes landing right on top of 60 hertz, which in the US here is our power line frequency. But that's a typical range for them. As I said, we can trap an ultra high vacuum, so that's better than 10 to the minus 10 torr for us. We can get perfect neutralization of the electric monopole moment of the particle. And we do that in the usual way by shining UV light either onto the particle or onto the pole pieces nearby, where we can then add or subtract one electron from the particle at a time, and we can see steps in the response to an electric field and stop when we hit no electric monopole moment. Of course, that doesn't guarantee that there's no electric dipole moment or higher order moments. We use linear feedback, which I've sort of diagrammed below here, to cool the particle's motion. We've gotten down to a temperature of about 140 microkelvin. And we do that in pretty much the usual way. We illuminate the particle from behind, typically now with a 785 nanometer laser. We collect the scattered light with some homemade optics and image onto some kind of position detector. And in my diagram here, it's a quadrant detector, but we often now just use a commercial camera to do this imaging. We take a derivative in some way, time derivative, to get the velocity and feedback a force on the particle. And we apply that force using one or more additional laser beams, control beams, typically at 660 nanometers in the red. And in this picture, we're only using one. In practice, we currently use typically 5 cooling beams and to do a little more complex feedback to all 3 degrees of freedom. And as I said, typically we can cool one of those degrees of freedom to 140 microkelvin. The other ones typically aren't quite as good as that, but typically down to a millikelvin or so, at least. So that's sort of the basics of our trap. We can trap particles, we can cool them, we can control them pretty well. These low temperatures are particularly for small particles on the order of 1.5 microns diameter and silica. So we put together data over a long period of time. This was from one of my graduate students' careers who later became a postdoc, so this includes some of his postdoctoral work. He assembled all of the cooling results he had from many particles, and we tried to estimate what the natural damping of these particles is in the trap under ultra-high vacuum as a function of pressure in the trap. So this is for 2 different degrees of freedom, this axial direction and the vertical direction in our trap. And we see, as expected, the damping decreases with pressure, but in both degrees of freedom, it seems to flatten out at some point and stop decreasing with pressure. And this might be because there's some other damping mechanism that's kicking in other than background gas, or it might be due to some limitations of our feedback cooling process, because these dampings come, in fact, from assuming that the damping rate with feedback cooling times the temperature with feedback cooling is the same as the natural damping rate times the natural temperature. And so that assumes 2 things. It assumes that the feedback doesn't add any extra noise into the system. And it also, in the end, we have to assume that the natural temperature would be 300 Kelvin, would be room temperature. And since we're at such low frequencies, any vibrations or other sources of interference from outside can easily drive the particle's motion. And so we might be seeing not, in fact, the damping just thermal motion, that is, but we might be seeing interference from things like vibrations. So that gets more complicated, and we're actually hoping to resolve some of those issues with some new measurement techniques in the near future. But we're still, the end here is that we're still far from the ground state. We're not close to a quantum system here. We still have occupation numbers on the order of 10 to the 5 or 10 to the 6. We think we're limited by lots of things, including finite vacuum still, noise in the system, vibrations in the room, which are difficult to manage at frequencies of a few hertz, and possibly rotation of the particle, uncontrolled rotation of the particle. So one of the approaches to getting around this, and I should say that even if we did everything experimentally perfect at room temperature, black body photons would still cause a problem and prevent us from getting to the ground state. So it was never realistic. So one way to try to get around this is just to hit the particle with more power to try to make radiation pressure shot noise more relevant. So to try to get into some kind of quantum regime. And in doing so, you inevitably do a faster measurement of the position. And the problem with that simple approach, at least, is that if you think of just trying to do the measurement faster, we very quickly run into the oscillation period of our particle. And in fact, the quantum decoherence time in our system is less than 1 oscillation period of, at least of the axial motion, which is the one we're interested in. So that's this sort of 10 hertz motion. And so this pushed us to start thinking about, can we make pulsed measurements of the system on timescales that are short compared to the oscillation period, where we start to treat the particle as a free particle. So now I'm going to jump from thinking about this as a harmonic oscillator to thinking of it basically as a free particle, because we're making measurements on a very short timescale. And the idea would be that you pre-cool the motion of the particle so it doesn't actually have a very large oscillation amplitude. and then do these sort of fast measurements. And in that fast measurement limit, there are three sources of noise that we really have to worry about. The first one is the usual radiation pressure shot noise. That is, you scatter n photons off the particle and you get a momentum kick due to the radiation pressure shot noise. The second one is the detected shot noise. So you can just use the minimum of the Heisenberg uncertainty principle to get an estimate of how large this is. This gives you a position uncertainty. So those are really, really standard. The third one's a little more complicated. It's thermal noise. And in our system, if you do even a simple estimate of the thermal noise, you find out that if you're trying to do measurements of the position of the particle at the standard quantum limit, that thermal noise dominates to such a large extent that you will never see quantum limited measurements. If you do then, one way to try to get around that is to do a sequence of two measurements really close together. And instead of measuring a position, you effectively measure a velocity or a displacement over a very short time period. It turns out that helps, but the thermal velocity is still effectively too large and dominates the measurement. However, if you do a series of three measurements and calculate something that looks like a finite difference acceleration, which we sometimes call the curvature of the position, you can then get to a measurement that is not limited by thermal noise. And this expression on the bottom is the calculation of thermal noise in this three-position measurement where you're effectively measuring the acceleration of the particle. So those are our three major noise sources. We can combine the three of them together, assuming that they're independent. And this expression that I have here includes some extra factors in there that make the measurement a little bit more realistic. So we calculate a number of things numerically for this. That includes using me scattering for the particle, because these are sort of 1.5 micron diameter particles roughly. So we're in the me scattering regime. We can numerically calculate the photon collection and detection efficiencies using, again, me scattering, Fourier optics, and some other simple numerical techniques, and estimate efficiencies for collection and detection. This is right now just for a simple 2-segment photodetector, which is not very efficient at collecting information from the photons. And we also can do numerical calculation of this thermal force and get a parameter in there. So this is how we estimate all the noise in our system. And here's what our measurements and estimates look like right now. So this green curve, which has on the x-axis, the horizontal axis has the detected scattered power in microwatts on a log scale. And then on the vertical axis here is the expected scatter in this 3-position measurement. So this is our curvature measurement in picometers. The green curve is what we would have in a perfect system with perfect efficiencies. And the orange curve is with finite efficiencies that we estimate for our system. And the blue points up here are actual measurements that we have so far. So they're not really that impressive because we're nowhere near the standard quantum limit, which is way down here, a couple orders of magnitude down from there. And so we tried to figure out, okay, why are we not doing as well as we'd hope in terms of getting close to the standard quantum limit? And these are, by the way, at measurements with a time scale of about 200 microseconds per measurement. So we analyzed the system pretty carefully. We checked out all of our electronics, which are shown in this lower plot. This shows all sorts of characterizations for our electronics. We found pretty much we had a shot noise limited detector and everything was working pretty well. So it's not a detector problem. We think that there are a couple things going on that limit our sensitivity at the moment. One is that, unfortunately, even an off-the-shelf silica microsphere is not really a sphere. It's slightly aspheric. And that causes variations in the scattering direction of the light off the particle as the particle rotates, because it's a slightly anisotropic scatter. Well, it's a me scattering, so it's a little worse than that. But the scattering direction in particular depends a little bit on the orientation of the particle. So as the particle rotates, the direction of the scattered light changes. And then through slight imperfections in our optics, the direction of the scattered light shows up as an apparent change in position of the particle. So we think that's a source of noise at low power. And then at high power, we think, again, this aspherical particle with some variation in the direction of scattered light is causing additional forces to appear on the particle that are pushing it around. So basically, if the direction of scattered light varies, then the radiation pressure on the particle varies, and that pushes it around. So this is what we suspect is going on. We're still investigating this and changing the kind of detector we use to try to get a lot more information. We're actually looking at using high-speed cameras for everything We're in the near IR, so cameras work, and we're still at a slow enough time scale that we can plausibly do measurements with high-speed cameras. So hopefully we'll continue making progress in this direction. We're getting to some tricky stuff, but I think we're making progress. Okay, so now I'm going to change gears here for a little bit and jump to some classical measurements. We're looking at measuring big G from the oscillation frequency of a particle between, it's basically just a harmonic oscillator between two big field masses. And we expect to see a change in the oscillation frequency when we bring those field masses nearby. This is purely classical for measuring big G. It's a very small frequency shift that we have to measure very precisely. And this gives a measurement of G from what's called the time of swing method. I'm not going to talk about that a lot, but it has motivated us to look at trapping large particles. In particular, in this case, we're looking at about 60 micron particles. You can see these pictures down in the lower left. And we track their motion, and we can track them over large distances simply by taking images on a camera and then doing a cross correlation between the images. And we've gotten quite good at this. And we recently showed that we can, through this cross correlation technique, track the position of the particle to about 1.6 nanometers in a single image. And what's kind of remarkable about this is that the pixel size in these images is about around 1 micron. So we're tracking the particle's position to about 1/1000th of a pixel, even though the particle's moving over many, many, many pixels. And we have evidence that works pretty smoothly. It takes an iterative method. We've developed some neat techniques there that work quite well. The nice thing is these work even with large particles, and they can work even, this technique can likely work even with somewhat irregularly shaped particles, as long as they're not rotating in an overly complicated way. We might even be able to pull out the rotation from the image analysis. Unfortunately, this does require a supercomputer to do this analysis, and it can't be done in real time, at least not right now.
Brian,
but we've thought of, yes. What was that?
3 minutes to go.
Okay, sorry, I'm slow. Okay, so we're also looking at using these trapped particles as an accelerometer. And I'm going to jump ahead a little bit and just show that we've actually done quite well matching the performance of a commercial accelerometer, looking at the motion of these particles in the trap. And they are absolutely, the motion is absolutely calibrated to within 3% relative to a commercial accelerometer. So we've published that recently. And so finally, let me get to the last thing. So we're now working on trapping silicon carbide particles that contain silicon vacancy defects. These defects are very much like NV centers in diamond, except the spin is 3 halves. So it's a little bit different. They emit in the near IR. The coherence times tend to be pretty similar. The contrast, if you're doing ODMR, is much lower, the optical contrast. So they're a little harder to detect that way. But we don't have any huge results in here, but here's what I really want to get to. Okay, so here's where we're going with this. We want to do electron spin resonance in trapped particles. We're not doing it yet, but we're working on it. There are 2 ways you could do that. You could do that with optically detected magnetic resonance, that is ODMR, in the trap, but the contrast is low and it's not really the way we really want to go. What we really want to do is something that I'm calling mechanically resonant Stern-Gerlach. It's basically a Stern-Gerlach effect. You flip the spin and look for a change in position of the particle in the trap, except that in our trap, it's quite plausible to flip the spin back and forth effectively at the vertical oscillation frequency of the particle. And because gravity biases the particle down in the trap into a magnetic field gradient, there's already a built-in magnetic field gradient in the trap to use for this Stern-Gerlach effect. So the basic idea is you let the particle get biased a little bit down by gravity into the magnetic field and magnetic field gradient of the trap. You shine the 785 nanometer pump laser on it, which reinitializes the spin to a plus or minus 1/2 m sub s level. And then you drive it with microwaves with a frequency modulated beam. And the modulation frequency is at the vertical oscillation frequency. And if everything works out, if you try different microwave carrier frequencies, you'll see a dispersive line shape of the mechanical response of the particle as you scan through the ESR resonant frequency. So we're going to be looking for a mechanical response in the particle at the resonant frequency as we go through resonance of the ESR resonance. And so this lets us use some Q enhancement from the motion of the particle, makes it a little easier. It also lets us use initially a large particle with a lot of these silicon vacancy centers in them. ultimately, our goal would be to switch to using a small particle with a single defect center in it, and use these high-speed measurement techniques that I was talking about earlier, this pulsed measurement techniques, to detect very small accelerations of the particle as you flip the spin. And of course, what we'd really like to do, our long-term goal, is to make macroscopic superposition states and all of that. Although it looks hard, but we're trying to build all of the pieces needed to do that in the long run. Okay, so I'd like to thank funding agencies, especially NSF and the 2.6 Foundation, have been funding my research for a while, and all the students who have worked on this. All right, thanks.
Thanks, Brian. Excellent talk. Really enjoyable. So any questions from the audience, please raise your hand and ask straight away. Yes, Dan, please go ahead.
Hi, Brian, really nice.
Thanks.
Sorry I bailed on moderating this session, but I'm in a budget meeting in the background. To escape that, I was, Dave Moore and I had thought a lot about these sort of pulse trains, and I was wondering, so, we were worried, I think, about heating in the sphere. So if you're pulsing at 100 microseconds, it's a lot of power, right? So do you ever encounter any problems?
It's a concern. I think we haven't seen any problems yet. Our power levels are not very high compared to typical optical trapping. So we're still scattering, on the order of a microwatt or something like that. It's not really an enormous power. So we don't see the particle getting damaged or melting or anything like that. Obviously, it gets a big kick, and we have to use some tricks to not excite it too much when it gets whacked with this pulse.
Okay, that's good news. Thanks.
Any other question?
I mean, I guess I can advertise that if you're doing those pulses, I mean, I like that you're saying I'm reading out the acceleration and I'm backing out the position, but you can also just say I'm measuring the acceleration. In particle physics, this is a very useful thing to do. Right? I just want a sharp impulse and I want to know if it happened. So.
Yeah, right. Well, I think we're used to thinking in picometers, so it's easier to put it in position units, but yeah, it doesn't really matter.
Andy, go ahead, please.
Hey, Brian. Yeah, really nice work. So I had a question about the plot you showed earlier with the measurement of the damping rate, and you showed that it deviated from the prediction at low pressures. So I was wondering, what was the method used to measure the damping rate in this case? Was it a ring down experiment or a line width, or how did you assess that damping?
Yeah, these are measured by line width. We typically don't have enough range to give it a whack and see. And watch it ring down. We haven't found that to work very well. So these are just line width, so they're not necessarily particularly accurate.
Okay, thanks.
Yeah. Now, keep in mind, we don't measure the actual natural damping. This is measuring the damping with cooling on, with feedback on. Without feedback on, the damping rates get to be too long. They can be, in some cases here, days. And so doing a measurement over a day or more with nobody slamming a door in the lab or sometimes in the building matters, it just doesn't happen.
Yeah, I can imagine.
Brian, I can't see any more hand, but I have a question. So really fascinating. I really enjoyed what you said. So one question I have is, suppose, because you might have heard that eventually if you want to do very, very sensitive experiment, we may have to go to drop tower. So my question is that suppose if in your trap, similar to Paul trap you had, am I correct? So suppose if I take G to be 0, can you test it? Can you do it? That would be great help if you can.
Can I drop the particle?
Make G 0. Can you do it? Some kind of like a, Yeah,
it's not something we've thought too seriously about right now. We use permanent magnets, and that makes it hard to even temporarily, drop the particle. We have thought of doing experiments in low Earth orbit or something like that, but that might actually be.
Or even in a balloon. Can you put it in a balloon?
The hard part in all of these things is that the process of trapping a particle is not automated. It's done, by hand, and then we have to pump out all the gas after. So anything that knocks the particle out in a single shot is not very attractive, or that you might lose it while you're taking off or something. is hard. So there's a lot of just experimental challenges there. There's nothing fundamentally that stops you from doing it. It's just work, just time.
Great, great. Good. In the interest of time, maybe I request Cristian Panda to share his screen, and let me thank Brian again.
Thank you.
So,
okay, so can everyone see the screen? Everyone see the slides?
And you are ready to go ahead, please.
Great. And I can advance them. And yeah, thank you so much, Anupam, and thank you so much to the other organizers and of course the discussion leaders for the invitation to be here today. So I'm Chris Panda. I'm a postdoc in the Holger Müller's lab at UC Berkeley. And I'm really excited to be here and tell you about how we probe gravity with trapped atoms. So we use this device that kind of puts a spin on atom interferometry. So instead of dropping atoms as is traditionally done, we do our atom interferometry on atoms that are instead held in an optical lattice. So, you know, we're all familiar with this stuff, so I'll kind of go fast, but motivation for some of the research that we do is because, you know, we're interested, of course, in finding the place of gravity, you know, within fundamental physics. For example, we know that the standard model of physics is incomplete. So, you know, there's kind of clear evidence that from astrophysical observations that points towards the existence of dark matter and dark energy. So this makes up almost all of the entire matter energy of the universe. But meanwhile, the standard model of particle physics only describes the regular matter, which only accounts for 4%. So far, terrestrial devices have been looking for the composition of the dark matter and dark energy, but haven't been able to explain its composition. So, you know, all of our evidence remains from astrophysical observations. So another question that we'd like to approach is about the unification of the 4 fundamental forces. So we know that 3 of them, electromagnetic, weak, and the strong, guide interactions at microscopic distances. And, you know, while there's still work to be done, they can be well described by quantum field theories, which is good. But in contrast, gravity is dominant at macroscopic and astrophysical scales, which is best described by the general relativity. So really the question is how do, and this topic of this conference is whether they can all be described by the same framework. And we sort of hope to answer these questions by developing precision quantum mechanical devices that can, you know, hopefully measure gravity. So some of the devices that we use are interferometers. And really the one showing here is the famous LIGO light interferometer, which is famously able to measure the weak gravitational signals from mergers of black holes. So sort of the working principle is simple. So you take a beam of light that you send over 2 different paths, and after traveling for a long distance along each path, the beam does get sent back and recombined into a photo detector, which measures the interference of the 2 paths. So the strength of this interferometer comes from the fact that the 2 arms are very long, in this case 4 kilometers, but really they have effective lengths of hundreds of kilometers due to build up cavities that are present in the 2 arms. So the wavelength of the length that is used can be very short, only about 1 micron. So therefore, a very small change at the level of the wavelength, or only a part per trillion, can make 100% change in the interferometer signal enhancement factor. So an atom interferometer is similar, but we built upon the idea of the wave-particle duality that was first introduced by Louis de Broglie's doctoral thesis. So the atom behaves like a wave, and it can interfere. So in a traditional light interferometer, you know, we use optical elements that are made out of matter to split, redirect, and recombine the light beams. But in an atom interferometer, we instead use light poles to split the atom in a superposition of 2 different spatial locations. And sometime later, we use the same light to redirect and recombine the atomic matter waves. So we separate the 2 output ports of our interferometer and then observe their fluorescence on a CCD camera. And the ratio of the 2 signals in the output ports is given by the phase accumulated during the interferometer. And in the case of a simple Mach-Zehnder interferometer, the phase is just given by kg t squared, where k is the momentum kick at each atom laser interaction, g is the local gravitational acceleration, and t is the time between the laser pulses. So, it's possible to use light to diffract atoms because we drive resonant multiphoton atomic transitions. that preferentially impart momentum to the atoms. And really the figure on the right of the slide shows such an atomic beam splitter or mirror. So we have a set of two laser beams that drive two photon Raman transitions between two long-lived states in an atom, which we just labeled G1 and G2. So now let's assume that the atom gets it's initially in G1, and if it's transferred into G2, it will not only have changed the internal state, but it will also have acquired a momentum kick, which is equal to 2h bar k from absorbing two photons. So a complete transfer constitutes then a mirror pulse, since it changes the propagation direction of the atoms. But if the transfer is not complete, then the atom can remain in a position of half G1 and half G2. So in that case, we can think of this as a partial wave function that is transferred. So the partial wave function that is transferred will change a propagation direction, while the one that is not will not. So that that corresponds to having a beam splitter pulse. So it's a beam splitter on the atomic wave function. So now, due to their sensitivity to gravity, there are many applications of atom interferometers in the field, and they have been used to measure local gravity, geophysics, and also inertial sensing. And the great example of this is really this compact interferometer that was built here in the Mueller lab at UC Berkeley. So it's small enough to just load in the back of the U-Haul truck, and you can drive it around the Berkeley hills. And using this device, they are able to measure the local gravity at different locations about their trajectory, and get information about the composition of the rocks underneath us, for example. So furthermore, this device showed enough sensitivity to measure the change in Earth's gravity due to tidal variations, and you can even show that this is sensitive to earthquakes that can occur, halfway around the Earth's crust, the underside of Earth. So atom interferometers have also, of course, found many applications in fundamental physics, and the great example of this is in the measurement of the fine structure constant alpha, which is also performed here, but also in Paris. So in this case, the atom interferometer is set up in a differential geometry in which Earth's gravity is canceled out. So it's now maximally sensitive to the momentum kick from the interaction of the atom with the laser fields. So this interaction is now proportional to the magnitude of the fine structure constant alpha, which dictates the magnitude of all electromagnetic interactions. So furthermore, you can also measure alpha separately in another system, in a panning trap, by measuring the electron's magnetic moment, as we heard on Tuesday from Jerry Gabriels, and comparison between the standard model, between the experiments checks the standard model theory and experiment with amazing precision of better than a part per trillion. So another example of is in the measurement of Newton's gravitational constant big G. This governs the strength of the gravitational interaction. So in this case, gravity, due to carefully configure source masses, is measured, and measurements of these big G's have been notoriously challenging due to the weakness of gravity in comparison to the other forces. But the atom interferometer measurement provides a competitive comparison to the traditional classical methods of using big G. So this is very interesting. And another example is in testing the equivalence principle. So in the simplest form, states that universality of free fall states that all objects must fall with the same acceleration, regardless of their inertial mass. And this kind of test was performed with two isotopes of rubidium, 85 and 87 at Stanford just last year. And it showed that the equivalence principle is valid even at 10 to the minus 12 sensitivity. So these are all really exciting and impressive measurements. So what are really they limited by? So in the case of atom interferometers, when you measure gravity, typically the main limitation is vibrations. And this is because you have instantaneous accelerations during each laser light interaction that gets imprinted onto the phase of the atom. So that means that any AC, or oscillating vibrations tend to obscure the DC, or the constant value of local gravity, by adding noise to your measurement. Now, for atom interferometers, such as the alpha measurement, or the big G, or the equivalence principle measurement, this run in differential mode. So the effects of vibrations and gravity are really canceled out. But in this case, the sensitivity is limited by the available free fall time of the atoms in Earth's gravitational field. So in a bid to really increase the free fall time, atom interferometry experiments have been growing increasingly tall. So there's a 10-meter fountain at Stanford and another 10-meter apparatus under construction in Hanover, China, and even larger apparatuses up to 100 meters being planned. But even for these large-scale experiments, the available free fall time limits the coherence to 2 seconds, really. So further increases in coherence time can only be achieved by putting experiments themselves in free fall, and this has also been done. For example, by using zero-G aircrafts, or launching the experiment in sounding rockets, or maybe you can put them in a capsule in a drop tower. And recently there's been the demonstration of the first Bose-Einstein condensate, which achieved in microgravity by the NASA Cold Atom Experiment at the International Space Station. So here at Berkeley, we take a very different approach with our atom interferometry. So we start with our experiment by launching an ultra-cold sample of atoms against gravity. So a sequence of 2 beam-swirl pulses separated by time t create the quantum superposition state in which atom is simultaneously at 4 different vertical positions. So we then select only the 2 atom interferometer arms in which atoms travel with the same velocity, are in the same internal state. And so far, this interferometer looks somewhat similar to traditional light pulse atom interferometers. And this is where we make a change. So at the peak of the trajectory, we turn on an optical lattice field that is sufficiently strong to hold the atoms against Earth's gravity. So the atoms are held now in a superposition state in which the 2 arms are separated by a distance delta z for time tau. So after time tau, the atoms are released from the optical lattice, and we do 2 final pulses which are separated by a time big T to recombine the wave functions. And this lists the interference. And we observe the interference fringes using really the same method that I described before. And unlike in traditional atom interferometers, where really most of the phase comes from the free evolution of the atomic wave functions during the hold from the interaction with the laser pulses, here most of the phase really comes from the fact that you have free evolution of the atomic wave function during the hold in the gravitational potential. So this phase is now proportional to the difference in the potential energy between the 2 interferometers, which are now separated by a distance of delta z. And it's shown in the formula on the right side. So how well does this do, right? So if we look at the contrast of our interferometer at the function of hold time, we see almost no decrease after 1 second. There's some change, so it starts to go down, about 5 to 10 seconds. But really, we still see coherence up to 20 seconds. So to put this in perspective, right, in a free fall atom interferometer, you will need a 500-meter tall tower to be able to achieve this. And this is, the height of really tall building like the World Trade Center in New York. And we can get the same sort of
We can't hear you.
Yeah, I was wondering if it's my connection or his. Yeah, but yeah.
Maybe he's frozen, but let's hope
Yeah.
he comes back.
Maybe he lost electricity or internet or something.
Yeah, it seems like, yeah. So let's wait. Let's hope that he will be back soon. Once it happened to me as well.
Hello?
Yeah. Sorry, we lost you.
Am I back? Okay.
Yeah, you're back. Please.
Okay, thank you. Sorry. Yeah, let me know if hopefully it goes well. So I was saying that we're still developing this device, right? And while we have shown our ability to measure Earth's.
If I may, your slides are not there. Could you?
Oh, okay. Yeah, let me just reshare. Yeah, probably they just disappeared. Okay. Are they showing now? Hopefully.
Yeah, we can see you. Yeah, we can see the slide.
Great. Yeah. So let me continue then. So while we have shown the ability to measure Earth's gravity, right, with this amazing coherence time of 20 seconds, we're still developing this device. So one of the limitations is that the coherence time is only possible of 20 seconds is only possible for a pretty small separation between the two arms of the interferometer of only about 4 microns. So what we see is that the interference coherence times decreases quickly as we increase the separation, as shown in this figure on the right side. So we see that the coherence time is really reduced to only a few seconds if we increase the separation between the arms to the tens of microns range. So what we do about this, so we have simulated the trajectories our atoms take in the optical lattice, and using the simulations, we have shown that the contrast decay can be caused by small differences in the holding optical potentials between the two arms. So this could become due to a combination of maybe 2 effects. So one is just imperfections in the optical potential from scatter and imperfections on the mirror surface of the optical cavity. And the second is due to the intrinsic wavefront curvature of the optical cavity. So we are addressing both of these decoherence mechanisms by improving the surface quality of the mirrors. So we're installing new mirrors and also reducing wavefront curvature by holding the atoms near the cavity waist. So we are in the process of installing and testing significant upgrades to this apparatus. So the new experiment has high quality super polished mirrors. The cavity is symmetric, so the atoms are held near the cavity waist. The mirror mounts we have already designed, and they have increased stability and reduced vibration. We have blackened baffles, which can greatly reduce optical scatter. And we also have optical access to transmission from our cavity, which we can use to monitor the profile of the optical beam while in our cavity. And in addition, we have made significant improvements to the vacuum system, which should allow us to diagnose it further. So we hope that this experiment upgrades will allow us to achieve even longer coherence times with increased arm separations. And with this increased sensitivity, the future looks good. And there are really many applications. For example, looking at an optical lattice interferometer that can be used for precision gravimeter by taking advantage of its compact geometry and immunity to vibrations. And a future application could be measuring the gravity of small masses. And this would take advantage of the fact that the atoms can be held now at a constant position near the source mass, so the interaction time can be maximized. And this would allow us to probe new energy scales for dark energy candidates, maybe the chameleon again, or we can also continue probing gravity at increasingly small scale. And another exciting research direction, it might be to measure the non-classical effect of gravity, so the gravitational Aharonov Bohm effect. So we could do this by assembling a source mass geometry as shown here on the right side. So by holding each interferometer arm at the maxima and minima of the gravitational potential, we could measure the potential difference between the two arms, really in the absence of forces. And this experiment could really be a new way to measure Newton's gravitational constant, big G, in the long term. So I'll also mention a recent sort of development. So an opportunity to test the quantum nature of gravity by measuring the entanglement between our oscillator and between a mechanical oscillator and our interferometer. So these ideas were already described better than I could ever have by Jake Taylor and Dan Carney at this conference, and they were published earlier this year together with Holger Miller. And without going into too much detail, the idea is that gravity is mediated between a high Q mechanical oscillator and our interferometer, and it would cause contrast decay and revival at the oscillation frequency of the mechanical oscillator that we could see in our interferometer. So possible experiment geometry might involve a hollow cylinder, which is made out of tungsten, maybe. It would oscillate along the longitudinal direction of our lattice atom interferometer. And in this case, the amplitude of the contrast or visibility oscillations is given by the coupling constant divided by the oscillation frequency. And we can make some estimates. If we assume room temperature maybe and a 10-second coherence time, we can now optimize the hollow cylinder geometry for each achieved interferometer separation to optimize the seen visibility change. So now the larger the separation that you can get in the interferometer, the better this gets. And this are separation that we haven't really achieved yet, not even with maybe 1 second scale coherence time, not even talking about 10 seconds. So this would require some work. But for atom interferometer separations, maybe of 1 millimeter, if you think you can get there, and then the contrast modulation could be in the 10 to the -6 range. So so it might be possible. It would be challenging to measure that small change. But
Chris, 4 minutes. Yeah.
Great, thank you, Anupam. But also, other challenges are this experiment would require pre-entanglement using a non-gravitational interaction with long coherence time, and probably also shielding to reduce non-gravitational forces due to electromagnetic or Casimir-Porter interactions, for example. But it might be possible in the coming years with the technique of this lattice atom interferometry really maturing and getting a lot more sensitive. So it's possible. It's something to look forward towards in the following years. And with that, I would just like to thank the people who contributed in this work. So Holger Müller is the leader of the group. There's Matt and Victoria, Sophus and Logan contributed greatly to the previous 22nd result. James, Miguel, and Andrew are working right now on new upgrades that we are installing right now. And I'd like to thank also the entire Müller group for their amazing support. And thank you very much for your attention.
Thanks, Christian. So it's very nice talk. So please, questions from the audience. Andy, I see your hands up. You have a question?
Actually, I had just left it up from the previous time accidentally, but yeah, so really nice work. I didn't have a question at the moment, though.
If there is no other question, the interest of time, maybe.
May I ask one question?
Go ahead.
Sorry for that. So, in the conventional atom interferometer, you want to wait for a long time to have the wave package to have large separation, so you can get a larger signal. But in this case, you can hold longer, but you have smaller separation. Will you really increase the signal from the gravity?
Yeah, that's a great question. I mean, we're happy with the 20 seconds, right? But as I mentioned in the slides, the problem is that we can only get the separation of 4 microns, which is not that impressive right now. And, to answer your question directly, I think if we can get an order of magnitude or even 2 larger separation, if you can get close to 100 microns, then I think this becomes competitive with the traditional methods. But right now, we're not really as sensitive to gravity effects as traditional interferometers. So yeah, we need to do work there. But if that can happen, right, there's obvious advantages. This could be a way smaller geometry. You don't need a big tower to get a long coherence time, and you have this nice vibration immunity. So it's that comes for free just from holding the atoms in the gravitational potential. So yeah, there's a lot of work to be done, but it's exciting. Mm-hmm.
Okay, yeah, thanks.
It also, I mean, the geometry allows you to integrate things close to a source for a long time. I mean, and which you just can't do with the fountain, right? So like that was why, yeah. I mean, that's an obvious comment, but.
Okay, thank you.
Is there any other question? If not, we move to our last speaker of the workshop, Nancy. Please, if you could share your screen. And thanks, Chris. Thanks a lot.
Yeah, thanks, Chris. That was a great talk. Actually, I'm not able to share. I think I have to be created a host. Someone.
So what, I think you have iPad or?
No, it's I think like I have to be designated as a host to be able to share.
Tiago, can you hear us? Could you make Nancy the host?
Oh, yeah. There we go. Yeah. Nice. Good. Okay, can everyone see my slides?
Yeah, we can see your slide, and yeah. So
okay.
Our speaker
yeah,
is
sorry. I like to use a weird aspect ratio for Zoom because like this is very impersonal way of talking to each other, but here we are. Yeah, today I'll talk about room temperature optomechanical squeezing. This is work that I did back in my PhD, but now I'm with Andy's group at Northwestern. And I'd like to thank the organizers for having me here, and I hope that all the people who stuck around for the last talk will get what they wanted from this. Okay, so this is like just the broad outline of what I plan to talk about today. I'll introduce the topic, and then I'll tell a little bit about how we design the squeezer and what things, maybe a little tidbit of what you could keep in mind if you want to design your squeezer, and then how we implement it in the lab, and the measurements of quantum radiation pressure and squeezing. If there is time and if people are interested, I also added 2 bonus topics which are more in the theme of this conference, which is basically like some recent limits on GR using gravitational waves, as well as some recent results on cooling kilogram masses to near ground states. So yeah, we'll see if we have time for that. But so basically, everyone has heard about LIGO. Everyone knows that what we're trying to measure is a very small strain. And in effect, what that means is we're trying to measure a displacement of something that's 40 kilograms to a level that's less than 1,000 times smaller than the proton radius. So when we start talking about measurements like that, we have to think about quantum uncertainty. And again, this is probably familiar to everyone in this audience, but essentially, when quantum uncertainty starts to matter, you can use squeeze states to lower that uncertainty and lower the noise. So LIGO uses squeezing right now to get a better noise performance. So what I've been focusing on for the last few years is actually using optomechanics to create a squeeze state. So the easiest way to understand optomechanical squeezing is just to think of a Fabry-Perot cavity where one mirror is fixed and the other mirror can move. So now the light that enters into the cavity has some quantum noise on it. And in this direction, it is sort of the fluctuations in the photon number. Now, every photon that bounces off these mirrors is going to impart some radiation pressure force just because of momentum conservation. And that force can be converted into a displacement if one of these mirrors is allowed to move. Now, that changes the length of the cavity, and the light inside the cavity, this delta X is the displacement. That's the quantum radiation pressure noise, in fact, that limits LIGO at low frequencies. So once you change the cavity length, the light inside the cavity is a standing wave. So that actually changes the phase of the light as well. So what that allows us to do is to use this radiation pressure force or this optomechanical interaction. It allows us to create correlations between the number and the phase quadrature of the light. And that's just another way of saying that you have a squeeze light. So this is how we plan to generate squeeze light. But we're not the first people to try and use the optomechanical interaction to generate squeeze light. There's these 4 beautiful experiments that have demonstrated optomechanical squeezing previously, but I'll focus on just one to drive something home as to what we are trying to do, how it's different from what's been done previously. So there's a few things in these experiments. First of all, they use a very high frequency mechanical oscillators, so in the megahertz, and they cool their experiments down, and then they measure the squeezing right near the mechanical frequency. So what that ends up making is that you end up getting this squeezing that's a very narrow band, because you're using the mechanical resonance of the oscillator, or you're using the amplification from the resonant features. So they're not able to do this broadband, and it has to stay at high frequencies because the oscillator is a high frequency oscillator. So what we were trying to do with this experiment is to create a broadband audio frequency squeezer at room temperature. Well, that LIGO already has currently, because crystal squeezers can do that. But the reason we wanted to go to optomechanical squeezers is we want something that can be wavelength independent. For example, for future generation gravitational detectors. So the idea is that we wanted to merge these two technologies and build something that really can do all 4 of these goals. Now, the problem when you try to do that is classical noises. So in this nice chain of correlations that I described, we can think of like classical noises entering and creating their own parallel chain of correlations. For example, thermal noise, and for example, laser intensity noise. So these classical noises create their own correlation chain, which then reduces the relative importance of the quantum correlation, and that actually reduces squeezing. So like this tells us why these other experiments were working in cryogenic temperatures, because they wanted to lower the thermal background, or why they were working at high frequencies, because high frequencies means it's easier for laser noise. You have lesser laser noise and you have less thermal noise at high frequencies too. So in this experiment, we wanted to be at low frequencies because, well, we need to make something for gravitational wave detectors. So that means that we had to design something that could work despite of the existence of these noises at room temperature. So that's the introduction. So if you've been emailing or something, maybe now's the time to get back on Zoom. So how do we design this thing? The main workhorse that I developed was this big optimization, where I took the optical parameters of the cavity, which is the mirror transmission, and the mechanical parameters of the oscillators, the geometry of the oscillator, and then looked at the squeezed field as a function of all of these parameters. And I asked the question, given the room temperature, given the frequency, is there any parameter space of these parameters that'll give me the squeezer that I want? And that optimization actually did result in positive results, but also it resulted in a lot of unintuitive answers. I don't have the time to go into the entire optimization today, but I'll just give you a teaser that, for example, we learned from this optimization that high finesse is not always a good thing for these experiments. So you might want to lower the finesse, and that's what we ended up doing indeed. To build a squeezer, we lowered our finesse from our previous experiments. But one thing for this audience that I will go into the optimization is the role of the optical spring in producing this squeezing result. So the optical spring is just sort of, you can define it as a spring that's arising because of the radiation pressure interaction. So the cavity has some response, the cavity power changes if you move the length of the cavity. And the change in cavity power applies a force by a radiation pressure on the mirrors. So you can write this transduction as basically an effective optical constant, spring constant. And so we call that the optical spring. Now, the interesting thing is that if you have a moving mirror, that will convert the force back into displacement. So that creates this closed loop that's closed by the mechanical susceptibility of this oscillator. And so now this closed loop, depending on the optical spring constant and the detuning, it can have a stabilizing effect, in fact, and we use the optical spring to actually lock our cavity. And I'm happy to go more into that later, but the optical spring actually provides a huge amount of stabilization in this experiment. But on a more fundamental scale, let's say we had a different way to lock the cavity. Do we still need the optical spring? And that actually goes back to the thermal noise problem. So the effective combined spring in the system can be written as the optical spring squared plus the mechanical spring squared. And to get this broadband frequency independent squeezing that we want, you want to measure that at frequencies less than this effective optomechanical spring frequency. And so this is one of the results of the optimization that I found, that the squeezing in the system can be parameterized by this dimensionless parameter that I call lambda thermal. That's basically, if the lambda thermal is high, then your squeezing is bad. If your lambda thermal is small, then you get good squeezing. So in that optimization, I was able to just have this one parameter that you can tune to reduce the role of thermal noise in your squeezing. And we see here that the thermal noise actually, of course, it goes as temperature, but it goes as square of the mechanical frequency. So intuitively, you would want to lower the mechanical frequency to lower the thermal noise if you wanted to keep the temperature fixed. But that meant that we wouldn't be, if we didn't have an optical spring, we would have to measure below the mechanical spring frequency. So if we pick a very large optical spring that allows the optomechanical frequency, the combined frequency, to be large, but still keep the thermal noise low. So just as an example, in our system, we picked the mechanical frequency around 800 hertz, whereas the optical spring is around 150 kilohertz. So that if we instead use the mechanical oscillator with 150 kilohertz without an optical spring, then the thermal noise in an experiment would be 35,000 times higher. So we wouldn't be able to measure any squeezing at frequencies in kilohertz region. So that's sort of the, I guess, one interesting aspect of designing this experiment. So now let's how we actually implemented this. So we designed the experiment, we locked this thing by radiation pressure, and then our collaborator Garrett Cole actually makes these chips for us that we had designed using the optimization. So the chips basically look something like this, where each of these little circles is one oscillator. Kind of looks like a badminton racket, just a floppy mirror. The mirror is made of algas and grass alternating layers, so it's a Bragg reflector. And the cantilever, the purple line here, that's just a gallium arsenide thin layer. And in each chip, we have about 100 oscillators because we wanted to have not put all our eggs in one basket. So there's a lot of variety of designs of this. And so the mirror diameters vary, the cantilever width thicknesses and width, not the thickness, the width of the cantilevers varies. And again, the length of the cantilever is also in the 100 micron range, but varies. The mass is roughly around 100 nanograms, and the frequencies of these devices are from a couple hundred hertz to kilohertz. So we have these chips, and we put them in this mount that holds the chip, and then we put it in the vacuum chamber with this mirror mount, and then we create a cavity with this chip by putting a fiber mirror in front of this chip, and that creates a small cavity between one cantilever and another curved mirror, and the light is brought into the vacuum chamber by a fiber and then exits in free space over here where you can measure squeezing. This fiber mirror technique is what I was building at MIT. But in the end, we actually went with a free space cavity technique for the measurements that I will show today, and those were developed at LSU. So the fiber mirror technique is still under work and gave us some technical headaches. But the fundamental physics of the chips was still okay. So now once we have the cavity, we can start to characterize the thermal noise of these chips. And what we found is this is the thermal noise spectrum of one of the oscillators on the chip that we measured. the pink is the measurement and the teal is the theory. And in the sort of 15 or so years of history of this experiment, this is the first time that we designed something and then we measured that it was fabricated, and we measured it to be exactly on top of the design. So we were really happy about that because that meant that a lot of different pieces that weren't quite going correct or in our favor in the past had finally aligned. So our knowledge was finally good enough, and our skill set in fabricating these things was finally good enough that we actually got what we wanted. And then, so once we have the thermal noise that we want, the next question obviously is, well, do we have the quantum behavior that we want? So we went and we looked for whether there is quantum radiation pressure noise in this experiment. So here I have the thermal noise in the pink again. That's the thing that we saw on the previous plot. And I have some classical noises in teal and the quantum noise contribution that's theoretical calculated in green. And the total theoretical noise you would expect to be in yellow. And one thing I forgot to mention in the previous plot is that this is the main fundamental mode of the oscillator that's around 800 hertz, as I said previously. So now we went and tried to measure the QRPN, and in fact, we did see that the total noise in the experiment did lie on top of the prediction. So that meant that yes, the quantum mechanical behavior of this experiment was also as we had designed or thought. But just to like emphasize again, this is like the first measurement of room temperature quantum mechanical radiation pressure in the audio band. So this was we were quite impressed by ourselves when we saw this. Now, if you have quantum radiation pressure and we had the thermal noise that we wanted, the next question was, well, do we have squeezing? So let's try to ask whether there was squeezing in this experiment. So the squeezing setup that we made was, again, we have this optomechanical cavity here. We send it some light that's intensity stabilized. And we lock this cavity, we take the light that's transmitted from this cavity, divide it into some small part that's sent back to lock the cavity. And again, this locking is via radiation pressure. And then we take the other piece of the light and we beat it with a local oscillator. And we use a homodyne detection there to measure what kind of squeezing we have. And if you notice carefully here, you'll see that this is not a balanced homodyne. This is a very highly unbalanced homodyne. In fact, we're only using one photodiode, but it is still a homodyne. And I'm happy to go into details of that later, but it was good enough for our purposes. So we tried to characterize what is the squeezing in this experiment, and this is what we found. So here on this plot, this is in decibels, so 0 dB means shot noise. So this is a shot noise measurement in yellow, and then in pink is what we measured in the squeezing quadrature at around 12 degrees, and in teal is what we expect when we characterize all the other noises in the system. Now, a few things to note here. First of all, the frequency axis is tens of kilohertz. So that means that we are very far away from the mechanical resonance frequency of 800 kilohertz. So this is truly now we're starting to be in the broadband regime where it doesn't matter where the mechanical resonance frequency is. Your squeezing is independent frequency of that. Then we have about 0.7 dBs of squeezing. And again, this was measured at room temperature. And the budgeted noise here tells us that we know exactly the technical noises in our experiment, and we do know what to do about them to lower them for the future generation experiments. This was the story in the squeezing quadrature, and now we can ask what is happening in the other quadratures. So here I'm showing as a function of frequency on the x-axis and the angle on the y-axis, the noise measured in color, where the oranges are basically below shot noise and pink is above shot noise. So again, here we see that like from 30 to 70 kilohertz, there's some squeezing, and that like it's maximum about 0.8 dBs or something. The top plot is the measured noise and the bottom plot is the budget. And again, this is not a copy-paste error. We just really understand our system really well. And now, anyone who has tried to measure optomechanical squeezing knows that one of the hardest problems of measuring it is to keep calibrating your shot noise every time you do this, because turns out that optomechanical squeezing is typically a bright squeeze beam. So you can't just block your, if I had to just physically just beam block my squeeze beam, I would not be able to characterize my shot noise because the power changes. So we were sort of annoyed by this every time trying to measure shot noise for each quadrature again and again, and it was becoming tedious, much to our dislike. So we asked ourselves, well, is there a way to measure squeezing without measuring shot noise? And we went back to the basics that squeezing is nothing but correlations. So what we do here is we take the beam that we previously were measuring right after the second beam splitter, and we put it on a 50-50 beam splitter, and we just measure correlation between these two photodiodes. And if you do some math, you'll find that, so here I have some vacuum, which is entering over here in this beam splitter, and here is my state that I'm interested in mapping. And I'm measuring the correlation between these two photodiodes A and B. So this is just a very simple quantum optics math, and you can find that this correlation C is basically a direct one-to-one map between the spectral density of this state X. So if the X state is squeezed, that is if Sx is less than 1, then the correlation will be negative. So and in fact, not just the sign, if you measure the correlation, you can completely back out how much squeezing you have in the system. So that's what we did. In fact, we measured this correlation, and this is what we found. So again, whenever it's negative correlation, we're measuring the sub-Poissonian statistics of those photons. And then we take this correlation function and we ask how much squeezing we have. And so that's shown here in the pink line, and the yellow is the squeezing that I showed in the previous slide. And again, this pink line is measured without measuring shot noise. So this is good for future grad students so that they don't have to go through the hard work of measuring shot noise for every measurement that they make. So if I have time, maybe I can go into the test of GR, or should I wrap up?
You have time, Nancy. Go ahead.
Okay. So I think in the spirit of this meeting, we were talking a lot about what kind of limits have been put on gravity and on quantum gravity. So I was hoping that the theorists in this meeting can shed some light onto how some of these limits that have been placed more recently and put them into context of these precision measurement experiments. So I've been thinking about these limits recently, and I think it would be good for this community to take these limits and put those on the plots that we typically use in the precision measurement community. So with the measurements of gravitational waves recently in LIGO, there's been a lot of tests that were performed for GR, and I've just selected a few here, but essentially there's tests that were performed on post-Newtonian corrections to general relativity. There were tests that were performed on the mass of the graviton. That's actually shown here is the wavelength, the Compton wavelength of the graviton. This black line here is the posterior probability that we were able to compute by using the first black hole event. So saying that the graviton wavelength has to be much larger than this, like 10 to the 13, 14 kilometers. And these are the previous constraints in colors from previous experiments. And so we've been able to put some constraints in this strong field gravitational limit of GR. And then also from the neutron star measurement, we've been able to put constraints on, again, on the post-Newtonian corrections on the mass of the graviton. But another interesting constraints that we've been able to put is on extra dimensions. So I heard some people talking about extra dimensions earlier in this meeting. So this is the constraint that was obtained on extra dimensions, where D is the number of dimensions. This RC parameter is the sort of length after which you get screening. The gravitational waves traveling at distances higher than RC will leak into these extra dimensions. And N is the steepness of the transition, again, into the leaking of the extra dimensions. So again, in this, we've been able to put upper limits on the dimensions, and we can see that the upper limit it's quite strong. Like only there's not that much scope of dimensions above, or depending on how big of RC you allow in your model. And then there have been also other interesting limits by combining all the black hole signals. And another interesting limits that have been put is on other theories of gravitation of GR, like the tensors, vector, scalar modes of gravitational wave polarizations. So I encourage people to go look at these, and maybe next meeting we can comment on how what implications do these limits have on experiments that we're performing in the lab. And some other limits that weren't really put by the LIGO collaboration, but these 5 papers appeared right after the first BNS paper was published. And in the spirit of this meeting, I went back and found all of my slides from a journal club I gave at MIT 4 years ago when these papers were published. But essentially, all of these papers were looking at the state of modified gravity and dark energy and dark matter after the measurement of this neutron star merger. And the idea is that basically all of these gravitational modified gravity theories have been ruled out, except for very fine-tuned ones that are shown in these colored graphs. Only those remain viable. And these authors very nicely also summarize the viability of which theories remain and which don't remain in this table. And this viability, the main limit actually comes from two different measurements. The first measurement is that of the time delay between the photons that arrive from the GRB. How long after the gravitational wave did the photons arrive? So what you can do is you can ask, the photons had to go through a Shapiro delay between the galaxy and us. So they had to go through a Shapiro delay. So these authors actually calculate the Shapiro delay very precisely. And then they were able to put a bound on violation of weak equivalence principle, that given that there was this Shapiro delay in the photon arrival time, and given that on Earth we measured the photons after a certain time, that tells us about this. That tells us something about this gamma parameter that you can use to violate the weak equivalence principle. And like, sort of for me, the punchline from this test is that if any of these models were correct, then the photons would have arrived 400 days after the gravitational waves were seen on Earth, and not like these few seconds after the gravitational waves that we actually observed. So this is a very strong indication that maybe these modified dark matter emulators, we need more work on those, or maybe we need to start thinking in other directions. The other measurement from this neutron star measurement comes from measuring the relative speed of the graviton relative to the speed of the photon. And so here's like how that speed changes in different theories of gravity. So essentially, this is the wave equation for how the graviton travels. And you have some parameter alpha t that modifies the speed of the graviton, and you have some parameter alpha m that's like the friction in the traveling of this wave. And you can measure the speed of the graviton relative to c because we saw both gravitational waves and photons. And then some of the other like Galilean gravity theories, you can define the scalar phi. And you can write this Lagrangian and the actions, and then you can derive the similar alpha t and alpha m coefficients depending on phi that you assume. And then you have some other theories that are the Horndeski and beyond theories where you generalize the G mu nu. Actually, you add these two new terms again as a function of some other parameter phi, and the gravitational waves would have to travel on a geodesic that's given by this. So if the gravitational wave speed was very close to photon speed, then that would mean, so first of all, if the gravitational wave speed was different from the photon speed, that means that D and E would have to be non-zero. But on the other hand, if the gravitational wave speed was same as C, then you start to need some like very interesting trickery to have the exact cancellation between D and E or between these two terms, because the tensorial structure of these two terms is different. So to obtain those exact cancellations, you're sort of A, fine-tuning, and B, those cancellations are not really robust against perturbations, and might cause interesting effects like speed be dependent on direction and stuff like that. So if you didn't want to have effects like that, then once you measure the gravity speed to be speed of light, then your only option is to just say D and E are 0, and so you're back to the normal general relativity. So in this case, by using this event, in fact, very strong constraints were placed on how different is the speed of gravity versus the speed of light, and that constrains these theories quite stringently. And so one other thing that I wanted to touch upon in again wrapping up this meeting is something that's been recently shown is to cool down the LIGO mirrors. So basically, these collaborators of mine, not me, they have taken the LIGO mirrors or the LIGO apparatus and applied feedback cooling to cool down this effective degree of freedom that's 10 kilogram. Basically, each mirror is 4 kilogram, and you're cooling down the differential arm motion, which has 4 mirrors of 4 kilograms. So you're cooling down the degree of freedom that's at 10 kilograms. And they've cooled it down to phonon numbers of about 10. So this is a very recent paper from earlier this year. But also, like, this is not a new technique. This was done actually back in the day by some of the same subset of people for initial LIGO, where they cooled down the initial LIGO test masses, which had an effective mass of about a few kilograms, 2 kilograms or something, to 200 phonons. But with advanced LIGO, with a very high measurement precision, the feedback cooling was able to be much better. So this is the state of the art. That if you're interested, this recent paper actually also provides this nice plot of comparison of what mass oscillators have been cooled down to what phonon application. I thought that was very useful. So yeah, just to summarize, I talked about optomechanical squeezing, and there are promising quantum resources for quantum measurements in the future. And we've demonstrated some room temperature optomechanical squeezing. We know what noises there are, and there's a lot of devices on the chip to actually make improvements on this. Thanks for the invitation. Thanks for listening to me. And of course, all of this work was performed with a lot of collaboration between a lot of people. So thanks to them as well. Sorry, I went a bit over time.
No, you're spot on. So don't worry. And thanks for giving a lovely talk. So please, questions from the audience. So I can see Chris and then Sugato. Please go ahead.
Yes, hi Nancy, that was a nice talk.
Thank you.
I wonder if you know about the work from Benno Hilke and from Hanover, basically, where they have these mirror that actually looks like yours, where they just bounce off the light and then measure the position from the radiation pressure. Could you explain to me, well, is there a difference, or are there any benefits from, because your setup looks basically more or less the same, but then it's not. So what is better? What are the benefits? What is
well, it's what they, if I'm thinking about the right experiment, what they are doing is they take they actually borrowed these oscillators from us. So I'm a co-author on that paper, and they're using they're using this these oscillators because they have such nice thermal properties to stabilize the laser power. So they've deployed these oscillators to create much better intensity stabilization systems because the thermal noise is so low. Yeah.
But aren't you also that's about bright squeezing in the end, isn't it? Isn't so?
They're not. So maybe I'm thinking of the wrong experiments because I haven't seen the squeezing experiment from Benno's group. I've seen the intensity stabilization experiment where they
actually. I see that you're actually on the paper. Yes, you are.
Yeah, it's not a squeezing experiment.
So you know what I'm talking about. Then,
yeah,
then
it
maybe
is
that's
intensity stabilization. Yeah.
Okay. Okay, then. Thank you.
Yeah.
Sugato, and then Andy.
Hi, Nancy. Very good, very interesting talk. So I will ask you about the thing you mentioned towards the end, this very heavy mass near the ground state, right? It seems almost like very strange. Like people work so hard to get 100 kilohertz masses to the ground state. So I was just wondering, what's the catch? Is it like thermalizes again back very easily, or is it the amount of laser noise or radiation pressure that you have to give?
Yeah, I mean, there is no catch. Interestingly, I think the instead of answering wrong with this, maybe I'm answering why they're able to
yeah, that's equivalent.
Is just very high measurement precision. So feedback cooling is only as good as you're able to measure the position of your oscillator. And in this case, we've got measurement precision of 10 to the minus 20 strain. So yeah, that's why.
Okay. And the standard quantum limit does not create any problem, or thingy?
It will. So yeah. So well, the standard quantum limit is good and bad, right? So given that we are at this measurement precision, there has been a parallel sister paper where they measured the SQL. So I guess that's a good thing. But yes, to move forward with this type of a feedback cooling experiment, eventually they do have to start worrying about the back action from the measurement. So they can't increase the measurement power too much because the back action will start to matter. But they have very carefully chosen the frequency band such that it's not a problem right now. Yeah.
Okay, thank you.
Angie, please go ahead.
Hi, Nancy. Always nice, impressive results on the squeezing work that you're showing. I just had a question about the prospects for kind of extending the frequency range. So you showed a nice, impressive band. Maybe it was between 30 and 70 kilohertz or something like that. What would be limiting you from going to say down to 10 kilohertz, or would that be technically what would be the challenge?
I'm trying to see if I included that in my extra slides, and I did not. So I'll just answer it verbally. So you're saying 10 kilohertz?
For instance.
Yeah, I mean, so 10 kilohertz is fine even with this generation of chips because we're limited by because our homodyne was outside the vacuum chamber. So we have some extra phase noise that's between the relative phase noise between the LO and the squeeze beam. So if the homodyne was moved inside the vacuum chamber, 10 kilohertz would not be a problem. To go lower than that, we really have to start changing these oscillators. And again, there's oscillators on this chip. So maybe in the next few years, Nurgis's group will demonstrate from these other oscillators better squeezing that goes to lower frequencies. But also, eventually, I think if we're able to build the devices that have a higher quality factor or a higher power handling, that would allow us to get even to 10 hertz. So the good thing is that now we have the recipe. So once we have these high quality factor devices or these high power handling devices, the theory is there, and we know exactly what we would build, and we would be able to get to 10 hertz and 10 dBs. So yeah.
Very nice, very nice. So let's go for the panel discussion, the last panel discussion of the workshop. Maybe I pin up other colleagues. I can see Chris, are you there?